Good morning, everyone. I have a cool little demo for you here. We have a copper chloride solution right here. And to it, I'm going to add sodium chloride. Take notes, please. Look at that. Very cool. Hey, that's a nice, pretty green color. Isn't that fun? Now, I'm going to add some water. Color shifting. And we're going to be talking about the chemistry behind this particular reaction. Let's see if I can make it a little more blue for y'all. There we go. That's a nice blue. Okay, let's take some notes. Do this and do that. Okay. So this reaction, the chemical equation for this reaction, we have Cu H2O plus 2 plus 4Co minus is in equilibrium with CuCO 4 minus 2 AQ plus 4 H2O. So we can see that over here we have our blue substances, our blue substance. Over here we have our green substance. And by adding to the solution, I can shift it between blue and green. And that's a really important concept of a famous scientist by the name of, and I apologize, their name is French. It's, I believe, pronounced Le Chatelier, but I'm not very good at pronouncing French names. That's my best. I unfortunately will probably pronounce it most likely Le Chatelier. That's probably how you most hear it. So this is Le Chatelier's principle. And Le Chatelier's principle says that when a system at equilibrium is under stress, the system will shift to overcome that stress. Right? So this kind of involves two things. There are two changes. There's going to be a stress, and the stress always brings the system out of equilibrium. And then the shift which always comes after the stress. The shift will always bring the system back to equilibrium. We should say change the system to bring it back to equilibrium. And color change is a great example. Let's say we have a beaker. Inside the beaker, we have a whole bunch of blues and one green. On the macroscopic scale, this is going to be observed as blue, right? If you have one molecule of green and a billion moles of blue, it's going to be observed as blue. And vice versa. If we have a beaker and we have a lot of green molecules, and one blue, this is going to be observed as blue, right? So the more blue we see, the more blue molecules there are, the more green we see, the more green molecules there are. More blue we see means more blue molecules. The more green we see, the more green molecules. Okay. So that's really important to remember for today for when we're looking at what's going on with the system. So I'm going to rewrite the equation down here. So here is our system, right? There is our system. We had green, we had blue. We started as blue. So we started as kind of this color right here. Started as blue. And then the first stress we did was to add sodium chloride to this equilibrium. Why is this a stress? Because sodium chloride isn't really in this equation, right? But we remember that when you put NaCl solid into water, it turns into Na plus and Cl minus. So really the stress was we increased the amount of chloride ions, right? So by adding NaCl, we are stressing the system by adding too many chloride ions. Now, what happened? What did we observe? The shift was that there was a change. The solution went from blue to green. How does that help us? How does that overcome the stress? Well, notice how Cl minus is a forward reactant. And to make something green, we want to produce more of the green stuff. For every one blue we're using, we're creating one green, right? And if we have too much of the Cl minus, what the system did, what we observed is that the system used up more blue and actually went ahead. More blue was used up to create more green. So because Cl minus is a forward reactant, because there was too much Cl minus, the system created more green, which uses up the extra Cl minus ions. So if we create more green, we're using up all of that ion. Okay. Then I did a second shift. Second stress. I added water, just plain old water. And we saw for the shift that it went from green back to blue. Once again, Le Chatelier says that when the system's stressed, it shifts to overcome the stress. We see that water over here is a reverse reactant. So it makes sense that if you stress the system by adding too much water, to overcome that stress, more blue and chloride ions, aka more of the reverse products, more blue and chloride ions were created to use up that extra water. And over here, we would call this a left shift. Left shift means that we are creating more of the left side of the forward reactants, and we're creating less of the forward products. Prediction time. Here's a tricky one. Let's do a third stress. What if I removed Cl minus ions? That's a stress, not just adding, but also removing. If I were to remove Cl minus ions, how would this system shift? Right. So let's look at this. The stress is that there is not enough Cl minus ions. What could we do to create more Cl minus ions? Well, we would have to shift to the left. If we shift to the left, that means that the color change we would see a change from green to blue. In other words, more blue would be created. There we go. Right? Because we don't have enough of the Cl minus ions, we remove that. So the system needs to shift to add more. It needs to create more of this side. And that's the tricky part, that it can't just create one substance. It needs to create either this side or this side, one side or the other. It shifts either to the left or to the right. You can't just create one substance. You have to create all the substances. And that's how Le Chatelier's principle will affect different equilibriums. Thank you so much for watching, and I will see everyone in class. Bye.